Hello everyone, my name is Zhou Chen from Tufts University and I'll be presenting on Spectra Explainability using Ontologies. Metabolite annotation refers to identifying the molecule responsible for a tandem mass spectra, and it continues to be a very challenging task for many reasons. The most common and reliable method by far is through library search, where the query spectra is matched against reference spectra in a database. Oftentimes, either too many or no metabolite is suggested by the algorithm. When multiple metabolites are recommended, understanding the fragments that produce the peaks can increase the confidence in the annotation assigned by the algorithm. This is known as fragment attribution. We can also utilize a large set of fully labeled spectra to gain insights into spectra where the molecule doesn't exist in a database through machine learning models. Current methods such as Magma, METFRAC, CFM-ID can provide peak labels given a spectra in its molecule, but the runtime for larger molecules can take substantial amount of time. For example, a single molecule that weighs about 500 Dalton could take over 30 minutes to process. This makes it very difficult to process a large data set such as the NIST 20 for machine learning applications. To label a large set of mass spectra, we propose using ontologies as a source for peak labels. Ontologies are structured classifications of chemical compounds based on molecular structure, chemical role, biochemical activity, etc. We're specifically interested in its classification based on molecular structure. For example, tryptophan is both a carboxylic acid and an indole, both of which are fragments of tryptophan. We identified two ontologies that are suitable for a task: Chebi ontology with over 11,000 entities and classifier with around 4,800 terms. Both data sources are well documented and thoroughly annotated, which allows our tool to easily extract the relevant information. Our tool is called Peak. In a high-level overview, Peak traverses the ontologies by looking up the input molecule in both ontologies. From there, a set of molecules that are structurally related to the input molecule is returned. Then, from that set, Peak identifies molecules that match to any substructure of the target molecule. These matching substructures are shown in the box. Finally, with a user-defined adduct type and tolerance, Peak labels the mass spectra peaks by highlighting the section of the molecule that produced the peak. To assess our tool, we checked Peak's accuracy against NIST 20, which has peak labels in the form of a formula. We attempted to label 305,000 N plus H spectra with a plus or minus 10 ppm tolerance, and we found that 16.8% of the peaks were labeled both by Peak and NIST. We then converted the molecular structure of our label to a formula and determined if our formula matched exactly, missed by 1 to 2 hydrogens, or completely missed against the NIST formula. We found that 55% of our labels match exactly with that of NIST labels, while 44% closely matched. Close matches are usually due to adduct formation or hydrogen rearrangements that are not represented in the converted formula. And in some cases of the mismatches, we noticed that the NIST formula did not represent a substructure of the parent molecule. They could be rearrangements, of course. But all in all, Peak showed 99.7% accuracy on the subset of NIST which it labeled. This shows that when a molecule is present in the ontology, Peak labels with remarkable accuracy. We conducted a second experiment to assess Peak's runtime with larger molecules. We randomly selected 520 spectra of unique molecules with masses greater than 400 Dalton. We then labeled these spectra with Peak and CFM-ID. Here is a plot of how the two algorithms performed at different masses. On average, CFM-ID took about 20 minutes per instance, not counting the 10 spectra that didn't process within 2 hours. Peak, on the other hand, took about 9 seconds per instance across all molecules of various masses. This shows that Peak performs consistently even for molecules of larger masses, which makes it feasible to label a large spectral data set for machine learning applications. In conclusion, we found that ontologies are a promising source for a large spectral data set which are suitable for machine learning. We presented a tool, Peak, that can traverse ontologies to identify peak fragments and label spectral peaks with high degree of accuracy. And while Peak's labeling capacity is limited by the ontology's limited vocabulary size, we are able to process larger molecule in a more feasible manner. As a future direction, we hope to build machine learning models to close the gap for peak explainability and spectra annotation for where a molecule is not present in an ontology or a spectra dataset. Thank you for your time and attention.